And please do not let me get into actual material without asking if I'm recording. Or you can probably see it on your screen, but I am. Especially next week, because I don't want Taylor to miss anything. Okay, so okay. Do we have any homework questions of any kind?
I have on the first one, 7.4.2.
Okay. Oh yeah. Okay, the error bound one. Yeah.
When I find, like in your, I was kind of following your example beforehand, and when I find the critical points and then I plug those in, like, so I think what I'm asking is if I get a decimal that doesn't turn into a fraction, should I trying to think of how to word this. I hate like not being able to show you, but should I make it like my number is 0.048? Can I just say less than or equal to 1/20, or should I keep it in decimal?
Oh, okay. Leave it as a decimal.
Okay.
Okay. Now, wait. Are you saying that was the final bound that you got?
No, just the part for the x times x minus 0.5 times x minus 1.
Ah. Okay. Hold on. I'm finding the actual problem here. Okay. So e to the x, second degree. What was that number again?
0.048.
Okay. Right. Yes, that's right. For that part of a problem. Okay. So I guess another way of rephrasing what you're asking is, are the numbers supposed to work out nicely? And I don't know if that was your angle, but it kind of sounded like it. And I guess in the numerical analysis world, it's hell no. That there are no nice numbers anywhere because it's a computer doing all the work and they don't care. So
I also wasn't sure, since it was a decimal, then I was wondering, do I need to round up no matter what?
I see. I would recommend rounding up in this case because we're looking for upper bound.
Mm-hmm. Okay.
But the thing is, this is something that we haven't gotten into in this class, but the nice numbers, fractions versus decimals, maybe think about it. Since computers are doing all the arithmetic in binary, that changes what is a nice number. So, like for example, just as 1/3 has an infinite decimal expansion, the same is true of a 0.1. So 1/10 has an infinite binary expansion. What I may do some, I don't know. I can't recall if in this class I did anything like. I know I've talked a little bit about floating point numbers and so forth, and I did that example of division without division. Okay. I don't think I've shown you all this, and it drives me nuts when I'm telling a student something and then I find that, I already told them. I hate repeating myself. So please feel free to stop me if I ever do, because one of my colleagues, when I was in my early years here, I heard every story he liked to tell, at least 10 times each. And I don't want to be that professor. I really don't. So, okay. Let's see. I'm going to MATLAB here. Okay. All right, let's. Okay, I think I'm. All right, I'll need my whole desktop this time. Come on. Okay. I can't really tell if this is working. Are you seeing my MATLAB? I didn't think so. Because I expect to see a little red on the side, and I don't. Oh, yep, there's no sharing at all. Gotta love Teams. It's like, no, I don't feel like it this time. Okay, let's try it again. Okay. Now, hopefully, you see my MATLAB. Okay. Now, the one time or another, I've probably shown you. Okay, if I assign a variable to be equal to pi. Okay, so what we have here. Oh, wait, hold on. I always forget to do this too. It's not the only thing I'm planning to do in MATLAB today, but okay, so if I set x equal to pi. So what we have here is when you type format long, because the numbers represent the same internally no matter what. And here we have 15 decimal places versus format short, and this you've also seen. Now, some other formats that I'm pretty sure I've not dealt with you is, well, this one came up. Oh, you did a format a problem in the MATLAB tutorial of that assignment where you had the Hilbert matrix and you displayed it in different formats, like format rat. I want to see what fraction it comes up with for pi. So a lot of people know of 22/7 as an approximation for pi, but here this one gets a little more accurate. So 355/113. But I'm going to show a rather unusual format. In the homework, did you have to do a whole format hex? Did that come up? I don't remember. Anyone? I'm going to take a look at the problem here. Because I think a problem called for you to display the Hilbert matrix in various formats. Okay. Oh, it just says in various formats. And one of those formats is hex. Now, hex looks like it's all gobbledygooky and kind of sci-fi. So there it is. That's the hex representation of the floating point number for pi. And, well, first of all, what is hex short for? What does that mean? If anyone knows. You might not unless you have a little bit of computer science background. It means hexadecimal. So this is base 16. So each one of these is a base 16 digit. So we have 0 through 9. And then to represent 10 through 15, we use letters A through F. Now, what's interesting about base 16 is, well, base 16 relates very closely to binary because every digit in hexadecimal is equivalent to 4 digits in binary. So I could, so it's a little easier to translate this into binary than numbers written in a different base. So I'm going to go ahead and do that right now. So if I have 4 in binary, is this text big enough for all of you to read? Okay. That's funny. Like I have MATLAB dominating my screen, and I have a Teams window in the lower right corner. And right now, I only see Chelsea. So you're speaking for a whole class. But I think sometimes it changes and shows someone else. But okay. So what do we have in binary? It would be, well, the number 4 in binary would be 0, 1, 0, 0, because I don't know how much exposure y'all have had to binary, and you treat it like decimal, but everything's in powers of 2 instead of powers of 10. So here we have the 2 to the 0 place, the 2 to the 1 place, the 2 to the 2 place, thus 4. Then these next digits are all zeros, 0, 0, 0, 0, 0, 0, 0, 0. And then this next one is 9, so that would be 1, 0, 0, 1. So 2 cubes plus nothing, plus 2 to the 0, which gives you 9. And then we have 2, 0, 0, 1, 0, 1, 0, 0, 0, 1. F is 15. Well, that's 8 plus 4 plus 2 plus 1. And then B is 11. So 8 plus 2 plus 1. And then so on. Okay, 5 would be 0, 1, 0, 1. 4 is, okay, we have a few 4s in a row. All right, and so on. I'm not going to do the rest of them. Does anyone see how I got from each of these individual digits to each block of 4? So again, each digit is a power of 2. Otherwise, you read it just like decimal. Okay, now from this, I can relate this to how floating point numbers are represented internally. The first bit, 0 in this case, that's the sign bit for this floating point number. 0 for positive, 1 for negative. Okay. The next 11 bits, in this case, it's a 1 followed by, so it's the rest of this. So 1 followed by all zeros. All right. Well, that would be, since there's 10 digits here altogether. No, wrong. Duh. What did I say? 11. 11 digits here. This is 2 to the 10th. Just as, okay, 1,000, 1, 0, 0, 0 in decimal, that's 10 cubed. So it's the same idea. So that's 2 to the 10th. So that's 1,024. Now, what does that mean? These bits represent the exponent plus 1,023. So in other words, you take whatever number is represented here, you subtract 1,023, and that's the exponent. So your floating point number is equal to -1 to the sign bit times m, which is a mantissa of a significant digits, times 2 to the e. In this case, e is this number minus 1023. So in this case, the exponent is just 1. Which makes sense because pi is 3.14, etc. So that's the number between 2 to the first and 2 to the second. Okay. So then the rest of these digits, so the remaining 52 bits, so that's all this stuff starting from here. Represent the mantissa, the significant digits of pi. Now, how do you translate those? Well, first, there's an implied 1. Now, think scientific notation. How's a number written in scientific notation? Like, if I have a number like, let's say, well, like 1,000,000 would be written as 1 times 10 to the 6. Like, there's always a normalization going on. Like, 314 to be 3.14 times 10 squared. So the first digit, to the one to the left of a decimal point, always non-zero. So the number is normalized. Here too, in binary, we normalize. The first digit, so the mantissa, I need to back up a bit. The mantissa is always greater than or equal to 1 and less than 2. So that constraint determines the exponent. So what happens is, because it's normalized to this range, just like in scientific notation, you normalize a number, you always have something between 1 and 10 times 10 to a power. So so the digit to the left of the binary point in this case can't be 0. What's the only other choice left? It's 1. So in decimal, you have some digit to the left of a decimal point that's 1 through 9. In decimal, binary, it's got to be 1. Since you know what the digit is, you don't store it here. It's implied. So mantissa is equal to the implied 1 plus the rest of the digits correspond to negative powers of 2. So like going from left to right. So first digit corresponds to 1/2. Then we have nothing, then nothing. Then the next digit, so this is 1/2, 1/4, 1/8, 1/16. 32, 64, 128. And then we have 256, 512, 1024, 2048, 4096. And so on. Yes, I know my powers of 2 pretty well because I was also a computer science major. And so on. So what I'm going to do here is I'm going to form this number. M is equal to 1 plus 1/2 plus 1/16 plus 1 over 128 plus 1 over 4096. I want to return to format long at least. Okay, so that's the number I have. What number does this appear to kind of look like? You might recognize at least the first few digits of this number. 1.57. Anyone?
It's like half.
Yeah, which makes sense because the mantissa would be pi over 2 because the exponent is 1. We got to multiply this by 2. So if e is equal to 1, then my pi is equal to the mantissa times 2 to the exponent. All right, I got the first few digits right at least, 3.14. But that's because I left off all these other digits, which there are 52 digits in total. So that's how a floating point number is represented internally. That we have one sign bit, 11 bits to convey the magnitude, to describe an exponent, a power of 2, that could be positive or negative. And then 52 bits specify significant digits in binary. So that's a typical format for a double precision floating point number. It's double precision because it's 64 bits or 8 bytes, whereas single precision is 32 bits or 4 bytes. So you have smaller range of magnitudes, not so many significant digits. But almost all computer arithmetic is done in double precision. Certain computer architectures will have extended precision. So numbers stored using more bits. All right. So I honestly wasn't planning to talk about any of this today. I'm honestly not sure what led me down this path, but then again, this is numerical analysis. This is an important topic within it. So it's a good idea. It's good to have some idea what's going on under the hood with the numbers that you're working with. And this came about because of this resulted Chelsea's question about decimals versus fractions and so forth in that one homework problem. So if I go back to format hex and I do like a negative power of 2, like 1 over 64. So what we have here is if you ignore the first 3 characters, the rest of them is a mantissa. There's nothing. Why? Because your mantissa is equal to 1. There's the implied 1, and then nothing more is needed because all the exponent alone is enough to describe the number. So what do we have here? 0, 1, 0, 0 for the 3, then 1, 1, 1, 1 for the F, and then 1, 0, 0, 1 for the 9. So the exponent is equal to this number. Wow, that's going to be a pain. Okay, I'll figure it out what it is. So the exponent is equal to, this is 2 to the 10, 10, 9, 8, 7, 6, 5, 4, 3. So I need to add up all those powers of 2. And then a 1. So that's the exponent. Ah, dang it. Okay. But then oh, that doesn't look right. 10, 9, 8, 7, 6, 5, 4, 3. Because I'm supposed to subtract 1023 from this. It doesn't look right at all. Oh, I know why. Yeah, I totally screwed up. That's not a 3 in binary, it's a 4. Okay, here we go again. Oh, now I see Walker down the lower right-hand corner. So you're a class spokeswoman now. Okay, so 3 in binary is 0, 0, 1, 1, and then I have all these 1s. 1, 0. Okay, so the exponent is equal to. All right, so this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 to the 9th, which is 512 plus. All right, so all these powers are 2. So 9, 8, 7, 6, 5, 4, 3. Plus 1. Okay, that makes more sense. Now the actual exponent, I have to subtract 1023 from that, and I get minus 6. What's 2 to the minus 6? Use format rat to see it as a fraction. 1 over 64, which is the number I started with. So when it's a negative power of 2, the exponent alone is enough to describe a number completely. There's no need for any significant digits. Just like in decimal, you have a power of 10. You don't need, it's just 10 to the whatever. You don't need significant digits to describe that either. On the other hand, if I take a number that is nice in decimal, 0.1, look at that. It's like a repeating it's like a repeating hex. So it's like 1/3. Like it's 0.3333 in decimal. So 0.1 in binary has this point. So really the pattern is this: the mantissa is equal to 1 point. There's the implied 1. 9 is 1001, 1001. So it keeps repeating like that, and so on until we have A. Well, A corresponds to 10. In other words, it's rounded up. So it's kind of like with 2/3. you truncate 2/3 and you get 0.666666667. It's the same principle at work here, but in binary. Okay. So now that I've consumed pretty much exactly half the class talking about something I had not even planned to talk about, but at least it's still a legit numerical analysis topic. Okay. One thing I want to do is something else involving a few items involving Hermite polynomials, which I talked about some last time. And since last time I had not recorded, just to have this on the record on video, okay. I'm giving a very quick recap here. So Hermite interpolation, as a reminder from last time, it's we have n+1 x values, and we have a polynomial of degree 2n+1 that matches of a given function f at those x values, and also matches a derivative at those same x values. So n+1 points, twice that many constraints, so 2n+2 constraints, so 2n+2 coefficients, therefore degree 2n+1. And the Hermite polynomial can be written in this Lagrange-like form. So you have your function values and your derivative values multiplied with these polynomials, the h's and the k's, that satisfy these conditions. So for the h's, it's a Lagrange polynomial at the x values, but its derivative is 0 at all of those points. So we have extra conditions. The k's are 0 at all the interpolation points, but the derivatives are like Lagrange-like, meaning they're equal to 0 at all of them except 1, where it's equal to 1. And how those were found, again, this is just a quick recap to get it on the record, that both families of polynomials can be expressed in this kind of form, because each one of these, the ith polynomial, it is equal to 0 at all the other x's, and its derivative is 0 at all the other x's. So in other words, if this is polynomial number I, xj is a double root. That's why we have its factor x minus xj squared. That's most of it. To figure out the rest of it, we need degree 2n+1, but this is only degree 2n. We add a factor of degree 1 and use the conditions that are satisfied at xi for the k's and the h's to figure out the remaining coefficients. So for k's, I had these coefficients ai and bi. For the h, I had these coefficients ci and di. So they have the same kind of form, and we just use whatever conditions that's satisfied at xi to solve for these coefficients, and that's what was done here. So, I mean, you have the details in your notes from last time. I'm trusting you all took good notes, but here you have everything. And I just wanted to give a quick rundown on the guiding philosophy behind finding these polynomials, that you use your knowledge of what is a double root to get almost the entire factorization. Then you have a linear, you have a binomial with 2 unknown coefficients to satisfy the remaining 2 conditions. Okay, now, so a couple things I want to talk about with, okay, so about Hermite interpolation. If my computer would not be so dang slow. Okay. So what about the error in the Hermite polynomial? Well, first I'll bring back a formula for regular or Lagrange interpolation. My computer is so dang slow right now, it is driving me crazy. All right, we have this error formula. So f of x minus Pn of x is equal to, we have n plus 1 factorial down below, and then we have for polynomial degree n, we have n plus first derivative at some unknown point that depends on x. And then we have a product of these linear factors involving all of the interpolating points. Okay, so that's what we had before. Now the error for the Hermite interpolating polynomial is very similar. All right, so our Hermite polynomial is h degree 2n plus 1. So because it's degree 2n plus 1, the derivative involved is one more, 2n plus 2. And then we have 2n plus factorial down below. And then over here, all these factors are squared. Okay. All right, so and which makes sense because I've talked about how oscillatory interpolation, it's like you're taking each of your x values. In the Hermite case, you're listing them twice, once for the function value, once for a derivative. So it makes sense that they would be squared in this error formula. Now, for the error in the original interpolating polynomial, I use this function phi of t, which is f of t minus Pn of t minus same thing as a function of x over pi n of x times pi n of t, where pi n of x is equal to, equal to a product of all the linear factors involving the interpolation points. Okay. Now, you can use a similar approach for the Hermite interpolation error, coming up with a function like this. Okay. Okay, and I actually want to add to this. Okay. Using not just this, but also repeated use of Rolle's theorem. Rolle's theorem is where the function is equal at 2 points, its derivative must be 0 in between. The reason why I point this out is this is one of the homework problems for section 7.5. So good luck. But this is in the notes how this was done back when I was covering. I think I'd done it after I finished covering 7.2, so it's from that week. You'll find it there. So the idea is in this homework problem to adapt this approach to come up with this error. So what changes would you make to your approach? And then again, a function like this, again using Rolle's theorem repeatedly. So it's a bit of a doozy, but let's see what you can do with that. So I just wanted to foreshadow that homework problem. Okay. Now, when introducing Hermite interpolation, I've shown like another way to get the polynomial is solve this kind of system of equations. So the top rows come from like a Vanderbilt matrix for matching function values, but then you have to change it to match to account for derivative values. So then you have this system of equations that you can solve. Now, in for regular interpolation, like Lagrange, you do have a MATLAB function that will handle polynomial interpolation for you, and that's Polyfit. But here's the problem: in MATLAB, as far as I know, anyway, I did check again, but I could try checking more fairly. I'm honestly not aware of a built-in function in MATLAB that performs Hermite interpolation or any other kind of oscillatory interpolation. It seems like a bit of an oversight. So what I want to try to show you in the last minutes that we have, okay, I still have 26 minutes. I want to come up with a quick MATLAB code that will do this, that will use this approach to perform Hermite interpolation. And to do that, you'll flip back to MATLAB here. I'm going to actually show you Polyfit. Now, because Polyfit is an M file, just like M files that you did for the homework. So any M file used to implement one of MATLAB's functions, you can look at it. So I'll open it in the editor. Now, what you see here is what you'd see in the help page. The help command, when it's applied to something that's in an M file, it's literally going to look for these comments below the function name and pull those, and that's the help page. So I want to skip past all of that. Now, there's a lot of gobbledygook here that unfortunately don't really have time to go into, but I can show you the main part of the code. Here, it takes your X values and constructs a Vanderbilt matrix from them. And then what it's doing is it's solving a system involving a Vanderbilt matrix and your Y values. Now, the approach involved here is it's actually a least squares problem because you're allowed to specify a lower degree than what we do in the interpolation I've described. So in that case, you get an overdetermined system of equations. It would solve at least squares, but we're not going to bother with any of that. Now, by the way, if you do take my class next semester, the 610 numerical linear algebra, I will talk all about least squares methods in that class. Also, methods for finding or solving eigenvalue problems, like computing eigenvalues and eigenvectors numerically, and I plan to work a little bit of machine learning as well. So there's my shameless plug. Okay, so I want to adapt this code. I'm going to copy. Actually, this is the only piece I need. Okay, so I'm going to implement a function first, my Polyfit. So a simpler version of MATLAB's Polyfit, where all I do is take X and Y values. So it'll compute the Lagrange interpolating polynomial Pn of X using a Vanderbilt matrix. It returns in power form. So it'll return a coefficient, so how polynomials are usually represented in MATLAB. Okay. Oh, yeah, I want to save it here. Okay. So first, I'm going to take those lines that I copied. Okay. Now, this Vanderbilt matrix is a little different than what I showed in my notes, because in that case, I had the first column, ones, second column, x values, then the x values squared, cubed, and so on. But here I'm going to do the columns in reverse order. Why? Because the coefficients need to be ordered from highest degree to lowest. So I create a Vanderbilt matrix that has the last column, column n plus 1, equal to ones. As a column vector, same length as x. Then I fill in the columns from the second to last all the way to the first. Notice I'm going backwards in my for loop. So what do? Each column is a 1 to its right multiplied by x. So I'm taking increasing powers of x as I go from right to left. This fills in my Vanderbilt matrix. Then I need to solve a system of equations, solve for coefficients. So Vanderbilt matrix times my vector of coefficients, P, is equal to the y values. But the thing is, I don't know if x and y are row vectors or column vectors. And I don't want to make an assumption about that. So what I'm going to do is, I want to make them column vectors if they are not already. How do I do that? I use a function that's mentioned toward the end of a MATLAB tutorial in the book called Reshape. I'm going to reshape x to have however many elements in x, that's how many rows. One column, that's a column vector. And I do the same thing for y, make it a column vector. Okay, so from now on, I can assume that it's a column vector. Why is that important? This is a column. I need this to be a column vector to carry out the appropriate multiplication. Actually, if I look back at Polyfit, I think this also forces it to be a column vector. So that accomplishes the same thing. I like typing this way because here it's more intuitive as to what's going on. Okay. Now I solve this system. MATLAB provides the backslash operator for that purpose. So P is equal to V inverse times Y. So the backslash carries out that inverse. So really it's doing Gaussian elimination and back substitution to solve a system. But I'm not done yet. I'm almost done. P is a column vector. I need P to be a row vector because MATLAB works with polynomials as row vectors of coefficients. So I'll just reshape it again to have one row and the appropriate number of columns. So this does the same thing as Polyfit. The only difference is it doesn't allow you to specify a degree. The degree is going to be n, no matter what. Okay. So any questions about how this was done for regular polynomial interpolation? I think I heard someone unmute themselves. Is there a question? All right, and of course I'll post this code, but because now what I want to do is I want to adapt this to the Hermite case. I'll call it Hermite fit. Okay, So I got to update the name. Now, here I'm taking x values, y values, and y prime values, the derivative values. So I'll make that a column vector also. Now, here I need a matrix that's double the size. The previous Vanderbilt matrix was n plus 1 rows, n plus 1 columns. Now I need 2n plus 2. Now, so what I'll do is, here, I'll fill in the last column to have ones, and then I will keep multiplying by x, like before, but I have to start from column 2n plus 1, go all the way down to 1. So if this fills in so it's not Vanderbilt, it's going to be Vanderbilt plus derivatives. The first half, the top half, it's like a Vanderbilt matrix. So I have 2n plus 2 columns, only n plus 1 rows, so it's the top half. And that part is just like a Vanderbilt matrix. We just have higher powers of x. So I don't have to change anything else in here. Now I need the bottom half. So what I'll do is I'll make a different matrix, V prime. Now for this matrix, okay, I have to be very careful here. The last column will be all zeros. Okay. Why? Because you're defining your polynomial to be like a0 plus a1x plus a2x squared and so forth. When you take the derivative, you don't have a0 anymore. It differentiated to 0. So that unknown plays no part in the bottom half. Because that coefficient is not part of a derivative. Now, the second to last column that will have all ones. Okay. So now what I want to do is, I'm going to go from right to left again and multiply by x. But I have to take into account the derivative. Now, so to do the rest of it, if my polynomial has this form, a0 plus a1x plus a2x squared, and so on, the derivative will be equal to a1 plus 2a2x plus 3a3x squared, and so on. So what I'm going to do is, because I have no a0, the last column of my bottom half is 0. Here I have ones. Then I have x, but times 2. All right, so let's see. So I need a loop. To account for the rest of the columns. Now, unfortunately, I can't just keep multiplying by x because I have a different coefficient every time. So what I'm going to do is I'm going to set a new vector xj to initially be x. And what I'll do in my loop is I'm going to multiply by x. Oh, wait. Okay, yes. Now, I filled in this column. I filled in this column, filled in this column. the next column is this. That's supposed to have 2 times x. So what will I do? My matrix, column J, that's the current column that I'm on, will be equal to whatever power of x that I have, initially just plain x, then it'll keep going up, times the proper coefficient. Now, how am I going to do that coefficient? My coefficients will be 2, 3, 4, and so on, increasing by 1. But the column index is decreasing by 1. So how do I figure that out? Well, I can look at some examples. Column 2n, the power of x is equal to the coefficient. Sorry, not power of x, coefficient of x. The coefficient is equal to 2. Column 2n minus 1, the coefficient is equal to 3, and so on. So the column index keeps decreasing. The coefficient of x keeps increasing. Can anyone see what a pattern here with these numbers? Like, what do they have in common? Like this pair of numbers versus this pair versus this pair. There's one property they have in common that I can use.
Grows by 1 each time.
I'm sorry, can you repeat the audios?
So, like on the first one, 2n, if you plugged in a 1, you would get 2. If you plugged in a 2, you would get 3 on the second column. If you plugged in a 3, you would get 4. So the n's going up by 1 each time. I don't know if that has anything to do with it, but
what to keep in mind is, because here we have decreasing by 1, here increasing by 1, what that means is the sum's the same. Here, if I add this and add this, I always get 2n plus 2. Why that helps me is I can use that to, since I have j here, I can use the fact that that this will be equal to 2n plus 2 minus this. So that 2n plus 2 minus j, my coefficient. So now I'm filling in the correct power of x and the correct coefficient that goes with it to have the count for derivative, a 2, 3, 4, and so forth. So now I have the bottom half of my Vanderbilt matrix. Now I need to stack them on top of each other. So V is equal to itself and then VP below it. Now, I need to solve a system of equations. Now, if I look back at what I had in my notes, I had the y values first, then the derivative values. So I need to stack them on top of each other as well. So I can do that down here. Y followed by y prime. So now I can solve a system and get my coefficients of my Hermite polynomial. Now, that's it. The code is actually ready to try. Does anyone have any questions about it before I do? I want to find an example that I can readily confirm. And I believe I have something handy. I just want to make sure it's in the right form. Okay. Ah, dang it. Okay. So I need it to be in power form because that's what MATLAB would generate. I'd like to have an interesting example, but I'm not sure what I do. And I have this, but that's not in power form. I could get it that way. Okay. I'll give this a shot. This is for the function involved is just something I made up. So here are my x values, 0 and 1. My function values are 0. My derivative values are 1. So I'll try that. And yes, I am setting myself up for embarrassment because I did not prepare this in advance. I've never written this code before. So we'll see what happens. My x values are 0 and all right. So f of 0 is 0. F of 1 is also 0. F prime of 0 equals 1. F prime of 1 is also 1. So my x values are 0 and 1. My y values are 0s. My y prime values are 1s. So now I can do p is equal to Hermite fit x, y, y prime. Oh, God. So if it goes wrong, I have 6 minutes to fix it. Dang it. Okay. Oh, I know why. I forgot to define n. Easily fixed. Because that means that this is wrong too. Oh, this is their polyfit. Oh, n is passed as a parameter in their case. I don't have it here. N is equal to the length of x minus 1. Okay, so at least there's something like that that's easy to fix. All right, let's try it again. All right, I have a solution, an answer, but it's in hex format. Let's put it back to format short and see what it looks like. Okay, 2 minus 3, 1, 0. Let's see if that's correct. The polynomial, okay, is here. All right, I have to multiply this out. So this is 2x cubed minus 2x. So then I have 2x cubed minus x squared. Oh, something's wrong. It's not matching. Now the thing is, I can't be certain if this is wrong or if everyone's wrong. What I'm going to do is I'm going to make some x values for plotting purposes between 0 and 1. Okay. Then evaluate this polynomial. Polynomial p at these x's. Okay. And then I'm going to plot it. And I'll see if it meets the conditions that I imposed. All right. It's equal to 0 at both points. And the slope, at least it's positive. So that helps. So that convinced me that this polynomial is actually correct. Now another way I can confirm, I'm going to evaluate the polynomial at my x values. And I get very small numbers, 0 and 0. Then I want to evaluate the derivative, polydir, at the same x values. I should get 1 and 1. Come on. I do. So actually, this polynomial is correct. So my code works. Now what went wrong here? let's see. Yeah, that's the data. So I need to find out. Okay. So my coefficients are 2x cubed minus 3x squared plus x. So I actually have almost everything right. My oh, wait a minute. I'm sorry, it is right. Oh god, I'm losing. Yeah. 2x cubed minus 2x squared. So therefore minus 3x squared in total. For some reason, in my head, I flipped a sign. Like I insisted on seeing this as a plus, and I don't know why. So, okay, it's the end of the day. Just put me down now. Okay, but it's at least now. At least when I was writing the code and writing this book, my brain was mostly working. So, okay. Well, we've run out of time, but okay. So now it's time to post all the things, and one of you has a class to run to. So I will, but I'll stick around for a bit for any questions. But I will stop the recording. Oh, actually, I'll keep recording in case anyone has any questions. But otherwise, off you go. Okay. So to any of the three of you who are left. Okay. Well. Okay. You're all gone.